Okay, well, we're very happy to have Dan Ramras here from IUPUI, and he's going to tell us all about stable representation theory and spaces of flat connections.
It really should be pronounced IUPUI, but
Ew.
That sounds even worse. So. Okay, so yeah, thanks for the opportunity to speak. It's the first time I've visited Sean here in Virginia, which is a nice place. So, all right. So I wanted to just start by giving a little bit of a broad overview of sort of how the ideas in this talk fit into a theme sort of in homotopy theory. And then I won't really talk about homotopy theory very much during the talk, but just want to sort of give this sort of theme. So the theme here is, well, co- or assembly maps. Assembly maps or co-assembly maps. And what are the ideas behind these maps? Well, so you have some sort of a homotopy invariant theory. So something that's not a homology theory. It doesn't satisfy excision. So you can't compute it just locally on your space and hope to get a global answer. But you can associate to a homotopy invariant theory an excisive, so excisive means satisfying excision, excisive approximation. And that's, well, homology or cohomology theory.
It's like pointer calculus.
Yeah, well, that's sort of an example of this theme. So in general, you get maps. Well, there's sort of assembly in one direction and co-assembly in the other. But you have maps connecting these things. And so the idea is that the difference between the homotopy invariant theory and the homology or cohomology, well, it sort of sees geometric information that's maybe hidden in this difficult to compute theory. So it sees some sort of geometry. So just to give you a couple of quick examples here. So in surgery theory, what one does is classify manifolds within a homotopy class. So you have some particular homotopy class, and you want to see what homeomorphism types, say, of manifolds or diffeomorphism types of manifolds exist within that homotopy class. And so the way this works is you set up something called L theory, which is homotopy invariant. It just depends on the fundamental group of your manifold. And then you have an excisive approximation. And there's some long exact sequence that whose third term is this object which classifies manifolds. So that's one context. Another is so algebraic K theory. There you get an assembly map where the sort of third term, the difference between these sides, classifies non-trivial H-cobordisms. So if you know about H-cobordisms, those are some nice cobordisms between manifolds. And in the simply connected case, Smale proved that they're all actually trivial in some sense. But when there's an interesting fundamental group, then you can get non-trivial stuff, and it's classified by understanding the difference between algebraic K theory, homotopy invariant, and some homology theory.
Algebraic K theory of what?
Of the fundamental group, of the group ring of the fundamental group. So your manifold. That's the homotopy invariant theory. So you take pi1 of the manifold, take this K theory group, and you compare it to some associated homology. And then there are fancier versions of this where you, so Waldhausen has a version of this, some results that he announced like 30 years ago that got published like maybe last year, in a book with 2 other authors. So he has a similar sort of theory that classifies sort of parameterized H-cobordisms, and also has information about automorphisms of manifolds, so, like self-equivalences of manifolds. So this kind of thing comes up a lot, and so today what I'm going to discuss is sort of relating representations. Well, maybe I'll say it this way: the difference between representations of pi1 of some manifold and the K-theory of M, which is basically a cohomology theory built from vector bundles. The difference between these sees information about flat connections.
Left-hand side is local systems.
Yeah, so you can think, there are lots of ways of sort of thinking about what the representations are, but we'll see. So for each representation, there is an associated flat connection. So it's natural that they should be somewhere in the mix, and by sort of working in this framework, we have sort of nice concrete statements about sort of the geometry of spaces of flat connections. So that's what I want to try to explain. Okay, so now I'm going to shift gears and talk about what these flat connections are. So I just want to give kind of just a kind of low-level description here that's kind of geared towards the ideas in this talk. So what I'm thinking about here, I have some manifold and I have some bundle over the manifold. You can think of it as a vector bundle. It's a little bit easier to say what I'm going to say if I think of it as a principal bundle. So it'll have some fiber, which is a Lie group. So over every point, I've got this fiber here, which looks like a copy of G. And so what am I talking about when I'm talking about a connection? If I have a vector here, a connection is this function which, given a point P up here in my principal bundle, it'll lift that tangent vector up here. This is like A at P of V. So it'll lift it up to some tangent vector on this bundle, which projects back down to V. So it's some way of lifting tangent vectors. And it's supposed to be invariant under the action. So if I were to go to P dot G, it's a principal bundle, so this group is acting. So if I go to P dot G, then if I lift at P dot G, if I lift the same vector there, that's just, the derivative of G applied to, the vector that I had there. So G just carries just preserves the whole picture. So that's the notion of a connection. So this is a connection. So what does it mean for a connection to be flat? Well, so now to say what holonomy is. So if I go around a loop in my manifold, then I can choose a point here, and I can lift that loop according to this connection, which means if I have a tangent vector here, I want on this lifted path for the derivative of this path to be the chosen lift of that vector. So I'm just sort of following some differential equation to lift this path. And when I come around to the other side, maybe I started at P, and here's this path gamma, and here's my lift, gamma tilde. It depends on what connection I'm using to lift the tangent vectors. At the other end of the path, I may not come back to exactly the same point, but it'll be in the same fiber, so it'll be of the form P dot G. And that element G is associated to this loop. So A is flat by definition if G depends only on the homotopy class, the based homotopy class of this element. And then we get a representation. So if you have any homotopy class in the fundamental group of your manifold, with this base point, say, then we can produce an element in the Lie group by just sending gamma to, well, G inverse as I've written it. Usually I forget whether there's an inverse or not, and I just say it's a 50-50 chance I got it wrong, but I looked it up this morning. So.
It's opposite.
Yeah, right. So if one can't tell the difference between G and its opposite, which sometimes I feel like I can't, then you really stop caring. But anyway, so to get a homomorphism, you just need to put an inverse there. Okay. So for every flat connection, we get this holonomy representation, as it's called. And so now we have so notation here. This is the space of flat connections. Space of flat connections. This musical notation is due to Tom Baird. Some of the results in this talk are joint with him. And this sits inside the space of all connections. And I should point out that this space, you can think of it as a vector space. Technically, it's really an affine space, but it's homeomorphic to 1 forms on the manifold with coefficients in the adjoint bundle of this principal bundle. So the point is that topologically, it's a vector space. Okay. So this object here is maybe one of the main points of interest in this talk. So I want to understand what can be said about this this space of flat connections.
You're literally just giving it the subspace topology.
Yeah, yeah. Mm-hmm. Yeah, so I should emphasize I'm not modding out gauge transformations. So there are automorphisms of this bundle, and it's a theorem that if you mod out the based automorphisms, then you recover the space of representations of the fundamental group. But I want to study this thing without any equivalence at all, just this sort of raw space of flat connections. Okay, so we'll see why that makes sense to do. So I want to talk about the case of surfaces. And so this all goes back to Atiyah and Bott. And they had the idea that when M is a surface, so M will be just a genus G Riemann surface, so this guy, G holes. You can study the space of flat connections by doing a sort of Morse theory on this big infinite dimensional vector space of all connections. So I'll explain how this goes. The Yang-Mills, so sort of what Atiyah and Bott said was that the Yang-Mills functional, which I'll define in a second, is a, in fact, in some sense, what they call perfect, quote, perfect Morse function on the space of all connections on a bundle over this manifold. So I'm not really going to get into this perfection business, but it's a nice Morse function in some sense. So what is this Yang-Mills functional? So this is called L. So L takes in a connection, and it gives you a real number, like an ordinary Morse function would do. So what do? You take your connection, and you look at sort of the size of the curvature. So to a connection, we can associate a 2 form that's the curvature. Curvature 2 form. And then you take a norm that depends on the choice of Riemannian metric on this surface, and you integrate that over the manifold. So key point is another way to define a flat connection is one that has 0 curvature. So the flat guys are exactly the guys that give you 0 in this integral. So the flat connections give the minimum critical set of this Morse functional. So you can hope that by doing some sort of, I'm not supposed to.
You say critical set, but the way you wrote it, it looks like it's just the zeros of the function instead of the critical locus.
Well, let's see. So the flat connections, it's the inverse image of 0.
Yes.
Yeah.
When you say the critical set uses image, it's like the inverse of the derivative.
Well,
DL.
let's see. So at that minimum, the function is always greater than or equal to 0. So this is the global minimum of the function.
Okay.
Yeah.
Yeah.
Yeah. So I'm integrating something positive. So the global minimum is 0, and so yeah. I mean, Atiyah and Bott, another thing they do is they describe all of the critical points of the Yang-Mills function, which are what are called Yang-Mills connections. So that was one thing that they did. And so there are other Yang-Mills connections with higher value of L than 0, but this is the minimum critical set. Yeah, okay, great. Other questions? So I want to say a little bit about what this Morse theory looks like in 2 dimensions. So Atiyah and Bott sort of set up a somewhat heuristic version of this Morse theory. I mean, they were able to prove some very nice things, but then Uhlenbeck and her students, Daskalopoulos and Rhoda, did a bunch of analysis that made it into a sort of a more honest Morse theory. So what I'm describing is also partly due to those people. Okay, so the picture here is we have this vector space of all connections, and it's mapping by L to the real line. And I don't really care about the negative part of the real line. There's 0. And so here's the space of flat connections, mapping to 0. And then, so what Johann Rhoda proved in this thesis is that there are well-defined gradient flow lines for this functional, and you can just sort of take a connection and flow it along these gradient flow lines until it hits a critical point. So this region here, those guys that flow down to the actual flat connections, and those are what are called the stable bundles, the guys that flow down to flat connections. But then maybe here's another critical value of this functional, place where the derivative vanishes. And so here are maybe more Yang-Mills connections that have that value. And then there's some portion of the space that flows down to there. And maybe this picture is a little bit misleading because what Atiyah and Bott showed is that all the non-flat or non-stable strata, so the strata are these sets, you fix a critical value and look at everything that flows to that value. All the non-stable strata have codimension at least 2 times g minus 1 times n minus 1. So n is, well, I'm thinking here of the Lie group being un. So these higher strata are in some sense very small. They have big codimension. And this is very much a 2-dimensional result. The gradient flow lines exist in 2 and 3 dimensions, not in 4 dimensions. But this business here, this uses complex geometry, so it's really a 2-dimensional result. Like it basically comes down to a Riemann-Roch calculation. They have a way of describing the tangent spaces to these strata, and they relate it to cohomology, and eventually they get a computation from Riemann-Roch. Okay, so the upshot of all this is that these sort of non-flat strata are far away. They're sort of way off in the distance, and so you can conclude here that the homotopy groups of this space of flat connections on this bundle are 0 for dimensions up to this bound here, g minus 1 times n minus 1. Maybe I should subtract 1. Maybe that doesn't even matter. Anyway, I'm not going to. All I care about is it's a big number. So I mean, loosely speaking, you're supposed to think that like these Morse indices well, the strata, the more strata sort of contribute their, I don't know, topology, their homology, whatever, with a shift in dimension according to their index. And so they contribute sort of way up at dimension at least 2 times g minus 1 times n minus 1. But in reality, there's a much more lowbrow way to think about it, which is you just take some class. Imagine you had some homotopy class in here. This is a vector space, so you just cone it off. And now, maybe it hit this stratum here, but this stratum was high codimension, and you use some infinite dimensional transversality to push it off. Yeah, so this is really transversality. Yeah. Mm-hmm. So, great. So what I want to talk about today is what happens for 3 manifolds. So the gradient flow lines still make sense. You can still define this Morse stratification, but almost nothing is known about it. Just that it makes sense to say, here's a connection. It always flows to some critical point, so you can break up the space according to which critical point you reach, or really which critical value you end up at. These critical Yang-Mills connections are not discrete. Okay, so we want to see what we can do here. And there's no complex geometry to be used, and so there have never been any calculations of like these Morse indices. Okay, so first thing I want to explain is some joint work with Tom Baird, which maybe I'll call parameterized survey theory. So what is this about? So there's this little construction which goes back to, well, all the way back to maybe 1958 from Atiyah, and then he and Sehgal studied it further. So given a representation from pi 1 m to, let's just say, un, from that representation of the fundamental group, we can build a bundle, E rho, and this bundle lives over M. And what is it? It's just the universal cover of M crossed with the group in question. And then I mod out the action of pi 1 m. So how is pi 1 m acting? Well, if I have a point M tilde and a matrix A, and I want to act by some element in the fundamental group, gamma, well, gamma acts by deck transformations on its universal cover, so I get M tilde dot gamma. And then this representation is exactly giving me an action of pi 1 on the unitary group by just translation. So it's just, yeah, it's just always a question of putting an inverse somewhere. I think that's the right thing to do, but I didn't look that one up, so I won't swear to it. You can put it on the left, you can put it on the right, you can put an inverse or not. I think that gives me a 25% chance of having it right. Anyway, so something like this. All right. Actually, I'm pretty certain if I do that. Whoops.
If you act on the right side, then it should be.
Yeah, exactly.
Inverse.
Exactly.
Right. Or you can just switch your action to the left action.
Yeah.
And then
it's not. I mean, yeah.
Then you worry about your quotienting on the right. You don't like the fact that you're acting on the left.
Yeah. So anyway, it's not a big deal. But so you can form a bundle like this, and this is actually a flat bundle in the sense that it comes with a flat connection, whose holonomy, in the sense I was describing before, is exactly rho. Mm-hmm. So you can get back from there to here. All right. So ordinary Chern-Vey theory tells you can compute characteristic classes of a bundle using a curvature form. And so in this case, the curvature form is trivial because the connection is flat. So the Chern classes of this guy, well, Chern-Vey theory is sort of a rational theory. So these guys turn out to be torsion. Chern classes are all torsion for all I greater than 0. Okay. So that's just the ordinary version. Maybe I can do better than this blue. So what about the parameterized version? So we want to understand like homotopy in the space of flat connections. And so to get at that, we need to think about families. So I'm going to start by thinking about families of representations. So we have a map from a sphere into Hom pi 1m to un. So this is like, you think of this as a k-parameter family of representations of the fundamental group.
And you're topologizing the right-hand side with using un?
Yeah, exactly. So if this guy has, like, if this is a group generated by some, I don't know, m elements, then this would be inside un to the mth power. Yeah. And that's the topology that makes this thing the quotient of the space of flat connections by the gauge group. Yeah. So okay. So now associated to this guy, we'll do something which I call the topological Sehgal construction.
Let's use the compact open topology.
It is also that.
It's the same thing.
Think of it sitting inside the set of all functions from this discrete group into un, and this set. The two topologies agree. That doesn't. Then you don't have to choose a generating set. Okay, so the topological Sehgal construction. So what this does is it builds a bundle now with a spherical parameter put in. So m tilde cross un still. And now this lives over sk cross m. And I have to mod out the action of pi 1m. And the action looks just the same. The spherical coordinate doesn't get moved. And so like if I think sitting inside here is some z cross m, then the part of the bundle there is exactly this guy E rho of z. So it's just a k-parameter family of these flat bundles is the way you should think about it. Okay. So here's the theorem.
So it's still just a vector bundle on a un bundle.
Yeah, it's still a principal un bundle. Yeah, I mean, you can kind of think of it as this parameterized family of un bundles, but it is still just a un bundle. The fibers are all un.
Same notation for representations in the parameter in the family.
Because I don't have a better idea.
Okay.
Yeah, yeah. I mean, yeah. I don't have a better idea than just still calling it rho. Yeah. I would be happy to have a better idea. So the theorem here is that study the Chern classes of these guys. The Chern classes.
E rho is what you wrote up there, even though you didn't put the same as E rho.
Oh, yeah. Sorry. So this thing is E of. So it's E rho, where now rho is this family. Yeah. Thank you. So these guys are 0 for I now bigger than k. So I guess. So k is this parameter here. So like here, this was like a 0 parameter family, and it was I greater than 0. Here it's a k parameter family, and it's I greater than k.
0 or torsion.
Yeah, right. In H star M Q. Yeah. Or I could have said torsion. Here I was more efficient. Yeah, so these Chern classes vanish rationally, or in other words, they're torsion, once you go above the dimension of the parametrizing family. And so this, the way this is proven, I mean, it's a similar idea. It's still applying Chern-Vey theory. The point is, the proof, just very briefly, you smooth out, I mean, this is kind of the hard part, smooth out rho in an appropriate sense, and then construct a family, well, a connection on E row that restricts, to, maybe I didn't name this. Here I said a flat bundle with flat connection. Yeah, I don't know. I'll call it, I was writing A for my connection, so I'll call it A associated to rho. So this one, now I have to say A row of Z on E row of Z. Yeah. Okay. So basically you can, those connections sort of make sense on each of these pieces, and what you need is to know that in some sense, as you move around in this family, those are changing smoothly. Once you have that, you can just sort of extend by a partition of choosing, you can just sort of make choices to extend the connection to the entire bundle. But the hard part is to set it up so that these things change smoothly. And that requires you to modify the original map row.
So the original map row is just continuous?
Exactly, yeah.
So but that modification, if I remember,
Yeah.
is very general in terms of this arbitrary,
Right.
real algebraic space.
Yeah.
So,
Mm-hmm.
so what prevents you from just having the same theorems that we replace UN by an arbitrary connected compact Lie group?
Right, so there should be some sort of statement there. The issue is, so then you're not dealing with UN anymore, so Chern classes aren't quite the right notion, but you can still talk about like characteristic classes of those bundles. And I certainly believe that there should be a theorem saying that those vanish. But I don't know how to prove it, because
Step one should still work the same, right?
Yeah. So there's sort of, so it's very believable. I mean, and there's actually a proof of this statement in that general context. So Camber and Tandoor have a proof of this statement that doesn't use Chern-Weil theory.
Yeah.
It uses some different sort of ideas, and they get a version for arbitrary Lie groups. I forget if it's compact, maybe compact Lie groups. So if one could somehow use their argument instead of the Chern-Weil argument at the end of this proof, so at the end of this proof you use Chern-Weil theory on this once you've constructed this connection. So it's very possible that this extends. I mean, I certainly think it should. But okay, so let's see. So here's another theorem, also from this paper of mine with Baird, which, so this is the part that I was sort of alluding to at the beginning, that by comparing somehow representations to vector bundles and looking at the difference, we'll see something about flat connections. So this theorem kind of is the first version of that. So if M is aspherical, which just means its universal cover is contractible, then, so I'm going to take a homotopy fiber of something. I'm going to take the representation space, pi1m to un, and I'm going to map from there to the space of based maps from M to BUN. Now, secretly, you have to think of M as being the classifying space of its fundamental group, which is another way of saying that it's aspherical. So this, you can think of this as the Grassmannian of n-planes in C infinity. It's the object that classifies n-dimensional vector bundles. But really, to make sense of this map, you should think of it as being the bar construction on the group UN. So then these are kind of functorially related.
So you're saying there's no other homotopy groups because of the fact that these universal covers both the possibilities.
Yeah. So this guy, this is just the KG1 associated to M, and that's what I'm assuming when I'm assuming M is aspherical.
So that's homotopy equivalent to M.
Yeah. So exactly. So what is this map? This map takes a representation rho and it sends it to sort of B row, where what I've done is I'm thinking of the classifying space functor as a functor, and associated to a homomorphism between groups, I get a map between classifying spaces. And so, okay, so what's the statement? So take the homotopy fiber at a representation row 0 in here, and this homotopy fiber is equivalent to the space of flat connections on the bundle E row 0. Okay, that's the statement. Now I should, just to demystify this a little bit, it's an easy thing to check that this map B row I'm talking about is a classifying map for the bundle E row. So you can think of this map, loosely speaking, as sending row to this bundle E row here. Just sort of choosing a natural classifying map for this out to the Grassmannian, loosely speaking. Okay, so somehow the difference, so this homotopy fiber gives you a long exact sequence from homotopy here to homotopy there to homotopy there, and then boundary map going down one dimension. And so what this is saying is the difference somehow between representations and these based maps, that difference is measured by the space of flat connections. And I should also point out that this is almost a definition. The homotopy of the based mapping space of M into BUN is just the K theory, minus K of M. There's some little caveat. N should be big enough relative to the dimension of M. N big enough. So this side is K theory. It's about classifying vector bundles over M. And that's the cohomology theory that we're sort of mapping out to here in that sense of assembly maps that I was mentioning at the beginning. Okay.
What's the difference between, there is a difference,
Yeah.
I'm assuming, but what's the difference between when you wrote pi m into UN, so
Yeah.
that you put some topology on there, and you can
Right.
So
Right.
This is, but you're only carrying this about this as a homotopy type anyway.
Yeah. Uh-huh.
You could also look at the unbased maps from M into BUN. So obviously you're not going to get everything. That's going to be a groupoid. It's going to be a one type.
Yeah.
What's the principal difference? Like what homotopy information is keeping the topology of UN around doing?
Well, so it's seeing these families of representations is what it's doing. So it's allowing me to think about an SK family of representations and form this parameterized bundle sort of out of it. That's maybe one answer.
I guess I'm really asking, but you can always postpone this to afterwards, but I just want to ask now.
Yeah.
As far as your explanation.
Sure.
So this space, you're running as a topological space, but
The Hom space.
right. I would be more happy if I could see it intrinsically, homotopy theoretically. Is there a way without using explicitly the subspace topology, you can just say abstractly what this homotopy type is?
I think the answer is no. I think that's kind of what makes this subtle. So you should think of this as this is the homotopy invariant theory that's hard to compute. And we're trying to compare it to something that's really honestly homotopy theoretical. I say it's homotopy invariant, but it's not homological, it's not excisive. So in some sense it's not homotopy theoretical in the sense of just coming out of standard homotopy theory constructions. It sees more about the group and UN than K theory or cohomology theories. And that's kind of why it's able to tell us something about the space of flat connections, maybe. Okay, so let's see. So I want to give an example of what this stuff tells us. So let's think about a 3-manifold. So M3 orientable 3-manifold closed. So you could think of like the torus, or I'm going to talk about the Heisenberg manifold, which is like you take this group of matrices where you have any real numbers up above the diagonal, and you mod out the subgroup where you have integers above the diagonal. So this is a discrete group, and this quotient is a 3-dimensional aspherical closed manifold. Aspherical again. Okay, so this is what I want to think about. So what we know here by orientability is that the 3-dimensional cohomology is Z. And that tells us that the rank of the first K-theory group of M is at least 1. So the K-theory sort of sees the cohomology in this way. And so that's saying that there's some class over here. And in fact, there's a class over on the right-hand side of that map in K-theory. So this is represented by some bundle over M. It's K1, so it's over S1. It's over the suspension of M, with C1 of this bundle equal to the fundamental class of the manifold. Equals the fundamental class of the manifold. So I have to match up dimensions here. C1 lives in H2 of the suspension, but then H2 of the suspension is H3 of M. Wait, what am I saying? That didn't get the dimensions right. 2, 4, 3. There we go. That looks better. Okay. The suspension shifts dimensions like that. So the second Chern class lives in H twice the dimension, and the dimension drops by 1 when I remove the suspension there. So now it makes sense to say that this guy is the fundamental class. But remember, if this bundle came from a family of representations, the theorem says that its second Chern class, 2 bigger than the 1-dimensional family we have, would be 0. So the theorem implies that E is not E rho for any family of representations rho from S1 into the Hom space. Because if it were, C2 would be 0. So I've produced some class for you over here that's not hit. So we have some E here that's not hit by this map. And then when you think about this homotopy fiber, well, if you have a long exact sequence, so if you have something that's not in the image of this, it survives to the next term in the sequence. That next term in the sequence is pi 0 of the space of flat connections. So sort of the boundary for that sequence applied to E gives you something in a flat, or pi 0 of the space of flat connections on this bundle, be like E rho of 1, where 1 is some point in the circle. And in fact, if you think about this a little more carefully, what you can see is that pi 0, so I could take any multiple of the fundamental class here, and what you actually learn from this is that pi 0 of that space of flat connections is an infinite set. So conclude pi 0, the space of flat connections, on just a trivial, just M cross Cn. I could write Un, but I won't worry about it. Is infinite. Okay, so unlike the case of surfaces where pi 0 and then a bunch of higher homotopy groups were vanishing. Here you have infinitely many connected components. Okay, so that's sort of the first difference between the two-dimensional case and the three-dimensional case. So when should I finish? Well, I mean, 5 or 10 minutes, is that?
Yeah, that's fine.
Yeah, okay.
I think you could go to 3:30.
Oh, okay, okay. That's
Comfortably.
great.
And if you want longer than that, maybe you can have a break and.
No, I mean, if people, I mean, I'm happy to talk, but I won't try to rope people in. Okay, so so I want to explain how to get more information than just this. Right now, this is just a pi 0 statement, and we're not going to get anything more from that theorem because what did I have to do here? I had to find cohomology classes in my manifold to use to sort of do this construction, and there is no cohomology in higher dimensions. It's a 3 manifold. So, I mean, I just want to talk today. I'm just focusing on 3 manifolds. So how can we get more? We want to get more info. Okay, so this is where the sort of stable representation theory comes in. So I'll just try to give a sketch of what this looks like. So we have this category R of gamma. So gamma could be any discrete group now. So this category, it's the category of UN representations. And n is not fixed here, so for all n. And isomorphisms between them. So just in the sense of representation theory, so some unitary matrix conjugating one representation to another. And so what sort of an object is this? Well, first of all, it's got a topology. Since there's an infinity theory person in the room, I will say it's an internal category in top. It's more than just a topological category. There's a topology on both the morphisms and the objects.
Okay.
So it's topological. It's just yeah, exactly. But it's also bipermutative. So what does that mean? It means that there's a plus operation, which is just block sum of representations, in form of block sum of 2 representations. And there's also a tensor product, which is like the Kronecker product of representations. You know, you can take the tensor product